Hello everybody, welcome back to our channels. Welcome back. It's first day again, it's the first day chemistry, okay? It's our third video. We are on S1.3 electron configuration, SL only. But this is a quick foundation, a very long video. I hope I can complete it once, okay? Or I hope when I edit it, you don't find it out. Okay, let's start. So first of all, we talk about emission spectrum. Emission spectrum is emission of light. So we need to have an understanding of what is light. Light is an electromagnetic wave. Later on, we'll treat it as a photon. And then you have to just have a basic understanding. Electromagnetic wave is the electric field and the magnetic field interlocking together and then propagating in the fast speed v. And then all the electric field, magnetic field, and the speed are perpendicular to each other. And the electromagnetic wave does not require the medium to propagate, so the light can pass through the vacuum from the sun to the earth to shine on us, okay? And electromagnetic wave is also called electromagnetic radiation. If you learn physics, okay, then you learn more about it. For chemistry, just this is absolutely enough. And then you need to learn about the electromagnetic spectrum. Light has different color, the visible light, and different color we call it have a different frequency of vibration or different wavelength. Okay, so electromagnetic wave show us the range of frequency for different kinds of electromagnetic wave. We divide them into different kinds. Okay, and they are the complete spectrum. We call it electromagnetic spectrum. And all electromagnetic waves that have the same speed in vacuum, we call it C. C is a constant, 3 times 10 to the power 8 meter per second. Wow, very quick, okay? So we have the equation C equals nu lambda. Nu is not weird, be careful when we talk about frequency. This is a Greek letter and we call it nu. C equals nu lambda. And the higher the frequency, this one you need to memorize it, is the theory, okay? The higher the frequency, the shorter the wavelength. Yes, they are inversely proportional because same speed of light in vacuum. And then next one is a higher frequency, higher energy. You need to remember it. Yeah, it's a fact, okay? And the visible spectrum, violet light has a higher frequency, so violet light is more energetic than the red light. And detail of the electromagnetic spectrum is given in the data booklet, okay? And in the syllabus, new syllabus, they use the frequency as F, okay? They change new to F, okay? So you might encounter new and F, okay? If it is the previous past paper, 2016 past paper, you see new, okay? New is a frequency, but now to 2025 onward, they change back to F, okay? So from radio wave to gamma wave, energy increases. From right to left, lambda decreases. Okay, in the data booklet, it is like this. Okay, very clearly, they show it from short wavelength to long wavelength. Okay, difference from the previous one. Okay, but this is what you will see in the data booklet. So from this data booklet result, okay, the data you will see the roughly range of gamma waves. Wavelength is about 10 to the power negative 12 to 10 to the power negative 16 meter. And then so on, okay? And the visible light is here. And you remember, the higher the energy, the higher the frequency, and the shorter the wavelength. So this part is the highest energy, okay? And for the visible light, start from the wild light to red. Okay, wild light is a 400 nanometer. You need to get this data from the data booklet. You need to memorize it, okay? And also in the number 3, okay, in the data booklet, I tell you about the metric. Okay, nm is nanon. Nanon is 10 to the power negative 9. So visible light is 400 times 10 to the power negative 9 meter. So it is 4 times 10 to the power negative 7 meter. Okay, and then this is an experimental fact. So when you heat up an atom, single atom or loosely atom, less dense atom, we found out that it has different emission spectrum. So we give heat energy to the atom, and the atom will emit the energy back as light energy, so we can see the spectrum. And this spectrum, each line is the emission of the light, okay? And the horizontal axis is the frequency of the light emitted. From left to right is higher energy, higher frequency, and shorter wavelength, okay? So for the visible spectrum, if we visible spectrum, the left hand side will be red and the right hand side will be purple. And there are two kinds of spectrum. One is night spectrum. This is a strange one. Only particular frequency of light is emitted for that gas, okay? Maybe for neon gas, okay, less dense, we give it energy and then it emits light. Only particular frequency of light is emitted. But in daily life, it is always a continuous spectrum. When it lights up a light bulb, it will give us a white light, right? So every rainbow colors of the visible light spectrum is emitted. Okay, all the color is emitted. So going to our eye, and the eye interpret it as a white light. Okay, so we call it a continuous spectrum. So it is a paradigm shift. Okay, our daily life experience is a continuous spectrum. We have a breakthrough in science by better observation. The spectrum becomes a night spectrum. We observe something more clear, and we find out it's a light spectrum. Okay, and we have some key terms come up. We call it the frequency of photons. In this part, okay, we find it our besides just the wave model for light, okay, we also need to use the particle model for light. So sometimes you will say light is a photon. We take it as a particle of photon, and each photon has energy hf. We'll encounter it clearly later. And then we look at the emission spectrum clearly. For example, the hydrogen spectrum, this ECS1, right? Only one electron and one proton, okay? ECS1, okay? We give energy to that electron, excited it to excited state, and then when it fall down, it emits light, and the light and the emission spectrum is like this, okay? And we see that, okay, the light spectrum, and the light becomes closer and closer together, and as the higher energy parts, okay, they converge. So many lines are so close together, they becomes a short continuous spectrum. We call it a continuum. Short narrow continuous spectrum, we call it continuum. So this is the experimental result, okay, really. And besides this series, we find our hydrogen spectrum even have a lower energy series, okay. So it has a several series of these kinds of light spectrum for hydrogen atom. And in the old time, you need to remember the name, Parson, Baumelt, and Nyman. But now you don't need to remember it, okay. You just need to know that there are different series of this kind of light spectrum for hydrogen atom. Remember, this is experimental result is a breakthrough, okay, for the experiments, and we have a theory, paradigm shift of the theory to follow it. And then how to make up our atomic model by this result, okay. So we said that the electron orbits around the nucleus in shell. So we said that the electron orbits around the nucleus at different electron shell. The shell are fixed. They can't evolve between two shell, okay. 2.5 shell low, 1.5 shell low, just 1, 2, 3 shell, okay. This is a shell model. This shell model, the result fits the emission spectrum. And then we said that the higher the energy cell, the far away from the nucleus, the higher the energy of the electron. Yes, I understand this thing. The higher the electron shell, the closer the energy levels, okay, because this has to fit the emission spectrum, right? The first gap is big and then smaller and smaller, okay. And then ground state is the state for the outermost shell electron in the atom, okay. This is the ground state, okay. And we can use this atomic model to describe ionization, okay. Ionization is making it a negative charge, negative positive charge, where it's removal of an electron from a gas, okay. And in chemistry, we say clearly. In other subject, physics, we don't say it like this, okay. We say clearly it's from the gas state. gas state. So first I make the atom in the gas state, and then I remove one electron from it, okay? All are in gas state, okay? So it's the first ionization. You got to remove all the outermost shell electron, and then you can keep on doing it, removing one electron and then removing second one, because it's second ionization. X plus become X2 plus. Even if ionization, X2 plus become X3 plus. You can go on. And then what is the first ionization energy? Okay, it means that you move the electron from this outermost shell to infinite. Okay, leave the atom. It means to the n equals infinite state. We call it ionization energy. And this is the energy you need to give the outermost shell electron to liberate it. So it is the absorbed energy. It's the first ionization energy. And in chemistry, we talk about not one atom, we find 1 mole of gaseous atom. Okay, 1 mole. So this linearity energy multiplied by the Avogadro number will be the first ionization energy. And the opposite is a electron affinity, adding an electron to a gaseous atom, making it a negatively charged. First electron affinity, X becomes X minus, gas state also. Okay. And then second is X minus to X2 minus, and so on. Okay. And the first electron affinity energy is the minimum energy to add 1 mole of electron to 1 mole of gaseous atom. So we add an electron to the next available place. Okay. And we call this energy, the emitted energy, electron affinity energy. Okay. So this is the electron affinity energy. So look at the arrow. Ions go up and then affinity go down. And maximum number of electron, it appears in 2024 May, so you need to remember it clearly, okay? And for different shell, okay, we call it a shell model, N1234, and you call this number principal quantum number. Sometimes in the exam paper, you see this number. Remember, this is simply N. N is a principal quantum number, big words, but just the N, the number of shell. Second shell, principal quantum number 2. Okay, don't panic. And the higher end means electron shell far away from the nucleus, right? Means a high energy, and the higher energy can have more electron there, and the electron in higher electron shell has higher energy. Okay, so each shell, okay, can hold 2n squared electron. You need to remember this. 2 is from the Pauli exclusion principle. Each orbit can have 2 electrons, and square is from the SPD number of orbital in different shell. Okay. You need to remember this 2n squared, 2n squared, 2n squared. So the first cell, only 2 electrons. Second cell, 2 squared, 2, 8 electrons. First cell, 3 squared, light times 2, 18 electrons. Fourth cell, last one, okay, 16, 32 electrons. So you need to remember this, okay. Remember this is for each shell, okay. And then for the emission spectrum, we can talk about it in details, okay, again, okay. And it is when the electron fall down from higher energy EM state to a lower energy EN state. We always say the EM to EN, okay. So the energy drop is EM minus EN, it becomes the electromagnetic radiation, and we call it 1 photon is emitted, and the photon's energy is HF, okay. And then when we heat up gas, okay, and then we correct all the energy emitted by the gas, okay, we call it an emission spectrum. Remember the lattice or the continuum. And then we talk about a hydrogen model, okay. N equals 1, 2, 3, 4, 5. Remember when it's going higher, the energy gap becomes smaller. This is to suit this experimental result, okay. And you find out so the N equal 1 and 2 are the biggest gap. This is the crucial part. So whenever an electron falls to N equal 1, the energy must be higher. Highest, okay. And the frequency highest, wavelength shortest, okay. So we have different series. So first, different falling, different combination, okay. You need to count how many possible falling of transition of the electron is possible, okay. And then we talk about spectrum, okay. First, second, and the third. Before we need to learn about the names, okay. So on the right hand side is highest energy. This is about falling to the N equals 1 state, okay. And this is the first ionization energy, is the continuum, right. This is the second series falling to n equals 2, so it is a second ionization and so forth. Okay, and remember, it's a convention. Left to right is high energy, high frequency, and a shorter wavelength. And then lots of theory. Okay, we have a summary later. Okay, the emission spectrum represents a vertically downward arrow. Remember, releasing energy, falling down is downward arrow. Just okay. And then the larger the energy gap, the higher the energy, and the frequency is higher because the energy of the photon is HF. We'll learn how to calculate it later. So the wavelength is shorter. Remember, higher frequency, shorter wavelength. Okay. For the first series is falling to n equals 1. Okay, it is the highest energy. So for the hydrogen, we will emit UV light. You need to remember this. Okay, for hydrogen, falling down to the n equals 1, highest energy, only UV lights will be emitted, not harmful to people. Okay, for n equals 2, falling down to n equals 2, visible lights, and you can see it. For n equals 3, become an infrared radiation, we can see it again. Okay? But no need to remember this, but we have to remember this fact. Okay? UV light, visible light, and infrared. This is the three series emitted by hydrogen atom. Other atom has other energy. We'll learn it later, and you can find it from the data booklet. So, and then the first layer is n plus 1 to n, right? Just one step up. Okay. Energy at a higher orbit is a convergence. Okay. Continuum. Okay. So converge at the higher energy. So converge at the right hand side, higher frequency and shorter wavelength part. Okay. So the energy of the convergent limit is the opposite of the ionization energy, falling down and going up. Okay, and this is all this thing is explained by the Bohr model. Mr. Bohr proposed this genius model to explain it. He said that electron in different shell with different energy levels, and energy level converge together as higher frequency. Actually, it is exactly the same behavior or the property of the light spectrum, right? It just uses a shell model of electron to explain it. So physics is chemistry is experimental result, experimental science. And then summary, make it simple. That's why it's too bad. Okay, summary. Okay, how to compare the energy? Okay, of the release of the energy. So first of all, be careful. Going down and going up. Going up is the absorption of the energy, right? Ionization energy. Going down is the emission energy. Okay, so be careful. Going up, don't choose it. Okay, so among the going down arrow, which one has the highest energy? So first look at the final state. If fall down to n equals 1 must win. Okay, must have a higher energy compared to falling down to n equals 2 and 3. So if n is the same, then look at the m. Okay, higher m, of course, higher energy gap. So the highest one is the 4 to 1. Okay, so look at the diagram and you can see it. Just make sure, remember the first gap is highest. Okay. And then color of the frame. Okay, this is a daily life application for this concept. In daily life, what is flame? Burning gases. Okay. Why it has color? Because we give the energy to the gas. Okay, burn it, and then the energy excited the electron to the higher energy state. When the high energy state electron fall down, it emits back, not it emits back the energy as light. Okay, and the light is HF. Okay, or H nu, and F is Hc over lambda. And then by the energy gap and all the constant, you can find out the wavelength of the light emitted is Hc over the energy gap. Okay, remember all these things you need to do some passive and lots of calculation. Very hard, very hard. And after you find out the wavelength, then you can go to the data booklet. And the data booklet are 15 of our 2251. Okay, tell you for different range of wavelength, the color of the frame is like this. Okay, from 585 to 647, it is orange frame. Okay, it is about the emission spectrum. Okay, later on we'll use this color wheel to talk about the absorption spectrum, opposite color. But now it's just simply which range, then which color of the frame. Okay. And we talk about the orbital. Okay, orbital is another concept because we said that okay, at different n, they can have a lot of electron. By n equals 1 2 electron, n equals 2, you can have 8 electron are not sub-electrons. So different electrons form different orbitals. So when we have a more detailed model of the atom, we don't n equal 1, 2, 3, 4, 5 is not enough. The main energy split out into sublevel S, P, D, and F. S is lower energy state, and then P, and then D, and F, and so on. Okay, and then F is higher energy. Okay, so as a sublevel has a one orbital. Okay, only, and then go on a P sublevel has a 3 orbital. Easy to remember. D is 5, F is 7. All are the odd numbers. Okay, and each orbital has 2 electrons. Can be inside it because the Pauli exclusion principle, spin up and spin down. Okay, and each orbital can hold a maximum of 2 electrons. So for the P orbital, it has a 3 orbital. 3 orbital, and each orbital has 2 electrons. So how many electrons can it hold? 6 electrons. For the D sublevel, 5 orbitals, 2 electrons, so 10 electrons. Okay, got it. And then we have a more sophisticated concept. We come out from the shell model, from the probabilistic model, and we call it probability of finding an electron at a particular position depends on its electron clouds. We draw at the electron clouds. Okay, we said that the electron is not exactly on that position; it just has a higher probability to be found as the orbital. And we have the electron cloud model, and different SPDF have different electron cloud shape. Okay. First one is like this. For the electron cloud is simplest one, closest to our understanding. It is a spherical shell. Okay, 1, 2, 3. Okay, so the 1s orbital is a sphere, so probably the electron is orbiting around here. Okay, you'll find the electron more probably here. Okay, on the spherical surface, it is symmetrical, so just 1 orbital. S is easier to understand. Okay. And we said that when we name these 2 electrons S1 and S2, use the superscript, okay? 1 and 2, okay? And then for the P orbital, it is a little bit strange. It is a dumbbell shape, okay? We said that if it is in a P orbital, it is more probably to be found on these 2 dumbbells, okay? And a dumbbell is a linear structure, so it can be along the x-axis, along the y-axis, or along the z-axis. So it has 3 orbitals, px, py, and pz. So for the P sublevel, it has 3 orbitals. Each orbital has 2 electrons, so altogether 6 electrons, and we name that as P1, 2, 3, 4, 5, 6. Remember, superscript at the right. The shape of the electron count in other D and F is our about zero. So you just need to remember S and P, okay? S is a sphere, symmetric, so 1 orbital. P is a dumbbell or ellipsoid, 2 ellipsoids joined together, so it has 3 orbital along x, y, and z direction. It's very important. It become a sigma and then the pi bond later. Okay. And then electron configuration. You need to draw out what is the details of the electron. Where is it? It is a spin up or spin down clearly by this electron configuration. It is a list out of all the electrons in an atom in an accurate way. Okay. First, we learn about Pauli exclusion principle. It said that each orbital has a definite energy, and each orbital px, py, pz can have a 2 electron of opposite spin. In Pauli's model, the electron is negative charge, right? Besides its spin, it circulates around the nucleus. It also spins by itself, but it can only have 2 spin. Okay, spin up or spin down. Okay, so 2 choice. One is spin up and one is spin down. So each orbital px, py, pz, or s is represented by a square. So inside a square can have 2 electrons, one is spin up and one is spin down. Spin up is a single side arrow up, not double side, be careful. It's the convention, you need to draw it this way. And then the other one is a single arrow down and the low arrow inside them, okay? So you need to learn, it is the 1s orbital is like this. And then when you draw the orbital, you have to write down its principal quantum number and it is sublevel on top of it clearly. So we call it an orbital diagram, very complicated. Then in IBDP, they'll give you marks, so you can write them down clearly. Orbital diagram. It is arrow in the box diagram like this, okay? And then too complicated, too hard to write, right? So sometimes they have a full electron configuration, symbol order. Just write down all this 1s2, 2s2, 2p, 2, 3s, and whatever. Make it simple. Just for example, oxygen. If it is a full electron configuration, okay, look at it from the data book, right? Okay, periodic table, oxygen has 8 electrons, okay, so 1s2, 2s2, and 2p4, okay, so altogether 8 electrons. This out, we call it a full electron configuration. For the full electron configuration, it's just the chronological order, okay, 1, 2, 3, 4, 5, SPD, okay, not about the energy. So the electronic configuration is a bit confusing. Maybe it is like this, okay, titanium 3d2, 4s2, but actually the 3d energy is higher than 4s in the empty orbital, okay. So sometimes it doesn't mean that a 4s has a higher energy than 3d, it's just a chronological order, okay. So be careful, don't get distracted, tricked by the electron configuration, not energy, just chronological order. So same number of electrons, same number of electron configuration, so the same number of arrangement, okay. And too big, sometimes too long. So we have a condensed electron configuration, okay. So to make the electron configuration shorter, okay, for the completely fully filled electron shell, 1, 2, 3, 4, 5, okay. And then we use the noble gas corresponding to it to represent it. For the sodium, it has 1 and 2 orbits completely filled. So we use the neon. Neon has exactly 1s2, 2s2, and 2p6, okay. Electron configuration represent the previous one, okay. And we just write sodium as Ne3s1, okay. Make it simpler and make it as short as possible. So we use the closest one, okay. So titanium is argon, not neon, blah 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 blah. Too long. We compress, we condense this one too. Do more exercise, do more possible, you learn it clearly. And then how to fill up the electron orbits, okay, from lower energy to higher energy. Before it's easy. And 2, 3, SPDF, okay. But there is some reverse, okay. Sometimes the lower principal quantum numbers orbits has energy even higher than the next one, okay. For example, 3D's energy unfilled is higher than 4s. Oh no. 4D is higher than 5s. Oh no. And then 5D is higher than 4F, and 4F is higher than 6F. Very complicated system. How to memorize it? Okay, I recommend you for this diagram. You draw it out. 1s, 2s, 2v, and then 2p, 3p, 4p between them, and then 3d between them. And then when you draw it out, look at this diagram clearly. The sequence will be step, and you'll find this sequence clearly. At first, when you do it, you need to look at this diagram and fill in the electron configuration. You do it several times, then you remember. I remember. Don't fill a 3D so early, fill a 4S first. Don't fill a 4D so early, fill a 5S first. And then 4D and then 5B. And then you remember it, okay. This sequence, you don't need to memorize it deadly, okay. Just look at this diagram, do more exercise, okay. Look at the periodic table, try to work on it, and then you will get it very quickly, promise. You're smart, okay. Okay, valence electron is the outermost shell electrons, okay. How many electrons in the outermost shell? 1, 2, 3, 4, 5. Later on, you look at the periodic table, you have to learn how to look at it, okay. This is just a theory. You don't need to memorize. You don't need to memorize like this, okay. Just show off our theory. Group 1 to 2, just the group number. Group 3 to 12, okay. We need to S2. And group 13 to 18, you need to minus 13, okay, because of the different group numbers. And IBDP requirement, okay, you need to draw all the electron configuration up to Z equal 36. So it's a huge exercise. You can do it 1 or 2 or 2 or 3 every day, okay, and then you work until you get a Z to 36. So work hard, okay, you will learn it quick. And then it is Hund's rules, okay, filling up the spin up and spin down state, okay, one by one, okay. The concept is fully filled shell is more stable. Halfly filled shell is also stable. So fill up the spin up state first, okay. Okay, so for the P shell, V spin up state has to be filled first, and then filled the spin down state, okay. Okay, like this, okay. This is the first principle for the Hund's rules, okay. Fill up the spin up state first, okay. Halfly filled, 2p3 is even is still more stable. Of course, fully filled is the most stable. Okay? And sometimes they even will borrow the 4s electron to it. Okay. For example, this one, the chromium needs to be 3d4, 4s2, 3d4. But you know that if a 3d is halfly filled, it will be more stable. So you borrow one 4s electron to it. Copper is also is to be 4s2 3d line. But you know that if my 3d cell is completely filled, it will be low energy. So it will sacrifice the 4s1. Borrow one and then become fully filled. So these two exceptions you have to remember. Okay. Just remember, half filled, fully filled is more stable. And then the other concept is different. Okay, we have the sequence. Remember, right? We said that 3D energy is lower than 4s, but it is only for the unoccupied state. When this is unoccupied, the 3D is higher energy than 4s. There's a reversal. Right? Normally, it should be 3D lower than 4s, right? But with this unoccupied, 3D energy is higher than 4s. But if it is occupied, the sequence comes back. 4s has higher energy than 3D. So when we fill the electron shell, use these rules, okay? Unoccupied. When we ionize the atom, use this concept because they are filled, occupied. So for example, if we have a transition metal like this, okay, argon 3Dn 4s2, okay? Be careful. The 4s energy is higher because it is filled. So when it becomes ionization, this 4s will go first, okay? So become 4s1 plus. And then becomes a 2 plus, 4s completely disappear. So this is the exception, okay? So be careful. Unoccupied, there is an exception. Occupied, no exception. The exception will reverse back. So be careful, reverse, okay? But it is in the 2024 May exam. So it will come back already. Be careful. And then the other thing is after we know how to fill the electron configuration, now is time to learn about how to interpret the electron configuration. They give you the electron configuration. So the last one is the outermost shell electron, and then they give you, and we add all the superscript is the total number of electrons. Okay? And those superscript, it means it's 1. Okay. And then if they are given the condensed electron configuration, okay, also add all the appears superscript. And also add the atomic number of A, okay? And then it will be the total number of electrons. And the farthest cell is at the right hand side, okay? Remember, not the lowest energy one, okay? And the period of the element period 1, 2, 3, 4, 5, okay, is the highest occupied shell n, okay? Highest n, okay? And the SPD block has started from group 1, 13, and 3, okay? Because of the design of the periodic table to include the transition metal 10 inside, okay? So the farthest cell X equals to SPD and then group, and then it will start from here, okay? It's a little bit, you look at the periodic table and then you know it clearly. And what's the valence shell? Valence shell is the outermost shell electron. And the number of valence shell is the sum of the superscript with the largest n, okay? All the 4 superscript add together is the number of valence electrons. For example, periodic table, okay? This is group 1 to be 1, okay? And this is period 1, 2, 3, 4, 5, okay? And for all these things is S1, S1, S1 is the outermost shell electron. This is 2, S2, S2, S2. Transition metal, they are d orbit. And the stability of atom, we talked about it already, okay? If all the electron is complete, okay? Atom is stable. If even all the electron shell complete, even more stable. So all the S cell completed stable, all the shells are SPD occupied super stable. So for this change to the ion, okay, the atom gains or electron. Just think about the destination and the starting point, okay. If the starting point is more stable, then energy is more, okay. If the ending point is more stable, then the energy changes will be less, okay. And we talk about ionization energy. When we talk about ionization, we need to do some calculation. But in the microscopic world, we need to introduce another energy unit because the joules is too big in the microscopic world. So we introduce energy, we call it electron volts, okay? And 1 eV is 1.6 times 10 to the power negative 19 joules, okay? But this energy is too small So they make it a mega EV, okay, multiplied by 10 to the power 6. So this is a more microscopic world energy, 1.6 times 10 to the power negative 13, okay. You need to learn how to transit, how to convert it between HF, HCl lambda, or a lot of calculation. Do more exercise, you learn it quick. And then ionization energy is from the ground state to the infinite state, right? And it is corresponding to the continuum's energy reverse process, okay. And remember, use E equals HF to find out the frequency of the photon emitted or absorbed, okay. Photon is the light, okay, and the Planck constant is in the data booklet. And also after finding the F, we can find the lambda by C equals F lambda. C is the speed of light. So you can see you encounter the calculation of big number and small number. So make sure you use your calculator more, get used to it, okay. And then about the trend in first ionization energy, you need to remember it, but the explanation is here. First ionization energy required to remove one electron from the element. Of course, this energy is about 1 mole, okay. And across the period, be careful this term. Across the periods, it means the same period, okay? From left to right. So period 1, period 2, period 3, okay? Be careful the word, okay? Across the period means same period. From left to right, okay? Because same shielding effect, but the number of proton increases, right? So the attraction of the electron increases, okay? So the outermost electron becomes more stable, so harder to remove it, okay. So the first ionization energy increase. So this diagram is easy to understand. Across the period, when the group increases, the ionization energy increases. This is talk about the S and the P one, not about the transition method one, okay. And then down the group, down the group means increasing the period, okay, from top to bottom. And then the outermost shell electron from equal 1 to 2, 3, 4, right, are far away from the nucleus. So the attraction of the outermost shell electron becomes weak. So the first ionization energy drops. Okay. Actually, it drops quicker than this increases, because it's one shell break. And then also remember, okay, the next ionization energy is highest if the atom or ion has the complete octet. Be careful. Look at the electron configuration of the ion and atom. For example, chloride minus, okay, it has a complete octet for the p orbital also, right? So its ionization energy, next one will be larger. On the contrary, if the atom or ion has one electron more than the complete octet, so it wants to remove this electron, right? And then becomes complete octet, so the ionization energy will be lowest. So remember, it is completely opposite, okay? It is the concept, okay? So think about whether it wants one more electron or it wants to release one more electron, or it doesn't want to do those, okay? Think about it by the complete octet concept, okay? Fully filled subshell concept, okay? Okay, this is the trend, the detailed trend across the group, okay? So you saw up and down, up and down, up and down. First ionization energy. The fully filled octet is more stable, so this is more stable. Even for the S fully filled is more stable too, okay? Half filled is also more stable, so PV is also more stable, 1, 2, 3, okay? And then there's a slightly drop from 15 to 16 because it comes from halfly filled to not halfly filled. Remember, one more electron, they hate it. They want to release this electron and then becomes just halfly filled. So this ionization energy will be a little bit smaller, but this drop is teeny tiny. Sometimes it's horizontal. Sometimes it's horizontal. And then the drop of the first ionization then repeats this period is small, okay? You see it later. Actually, the big jump is across the period, okay? And 1, 2, 3, 4, 5, okay? And it is shown from the data booklet, okay? If you don't remember it, just look at the data booklet. And then first ionization energy is on Park's line, okay? And you can see down the group, wow, big job, okay? Ionization energy, top left corner. 1,300 become 500, 400, and 400. Wow, big job. And across the period to the different groups, just a small drop, okay? a big drop too. It is completely a big rise, okay, because the S shell is complete, okay. 500 become 900, wow. 500 becomes 700, 400 becomes nearly 600 because the S shell is the sublevel is completely filled for this one. On the right hand side is clear too, okay. You can saw the trend, okay. Down the trend, big drop. Up the trend, it do increase, okay. So increase, and a slightly drop here. Remember, nitrogen, phosphorus, and AS is the P shell is halfly filled. So one more electron, they don't like it, so drop a little bit. They want to release it again. So rise, drop, rise. So you can see the trend clearly. If you don't remember that diagram, you can remember, I'm sure. Then look at it from the data book for emergency, okay, in multiple choice question. Okay. Thank you. That's all for my sharing. It's a long one, okay. You need to maybe you need to watch it again, okay, probably, okay, and then maybe and then you go to internet, find some exercise to work on it, okay, and I'm sure you can learn very well. Okay, if you like our sharing, okay, remember subscribe and like it, and then share it with your friends. Okay, see you for next video. Bye.